Before we look at the problem, let's understand a few key points first. This type of problem asks us to look at position, velocity, and acceleration at the same time. These are connected through the function, its first derivative, and its second derivative. 3 reminders will make solving much easier. First, the position function can be quartic, cubic, quadratic, or even linear. What matters is the y value against time. For straight-line motion, the y value is distance from the origin. For a projectile, the y value is height above the ground. Second, always sketch the overall shape of the graph. Focus on critical points, inflection points, and where the graph crosses the axis. Exact numbers are less important at first. Third, remember the connections. A critical point of the position function means velocity changes sign, so direction changes. An inflection point of the position function lines up with a maximum or minimum of velocity, and that's also where acceleration changes. Sign. Pre-check before question 1. Look at the position graph. At time 0, did the object already begin moving, or did it actually start its motion at that time? At time 0, the graph shows the position of the object at y equals 8, but the velocity at that time is not necessarily 0. This means the object may already have been moving before we started measuring. In other words, time 0 is simply the moment when we begin our measurement, not necessarily the instant when the object first started its motion. So the answer is, the object had already been moving, and time 0 is just the starting point of our observation. Question 1. On the graph, what are the object's starting position at time 0 and its position after 9 seconds? The position is given by the y value. At time 0, the graph shows the position is 8. At time 9, the graph shows the position is 6. So the two positions are 8 at time 0 and 6 at time 9. Question 2. At what times does the object change its direction of motion? The object changes direction whenever its velocity is 0. At those times, the sign of velocity changes, which means the direction of motion changes too. Velocity is the first derivative of position, so we look for the zeros of that function. From the graph, this happens at times b, d, and f. So the object changes direction at b, d, and f. Question 3. At what times does the object reach its maximum speed in the positive direction and in the negative direction? Note: the greatest negative speed should be considered between the time when the object has gone the farthest in the negative direction for the first time and the time when it reaches the farthest point in the negative direction for the second time, measured from the origin. Look at both the position graph and the velocity graph together. The velocity reaches its maximum or minimum values at its critical points, which occur when the acceleration, the derivative of velocity, is 0. From the graph, the velocity has a local minimum at time c and a local maximum at time e. Therefore, the object reaches maximum positive speed at time c and maximum negative speed at time e. Question 4. At what time does the direction of the acceleration change? The direction of acceleration changes where acceleration is 0. At those points, the sign of acceleration flips, so the direction reverses. Acceleration is the derivative of velocity, or the second derivative of position. From the graph, this happens at times c and e. These are also the inflection points of the velocity graph. So acceleration changes direction at c and e. Question 5. What is the relationship between the inflection points on the position graph and the corresponding times on the acceleration graph. An inflection point on the position graph means the concavity changes. Mathematically, this occurs when acceleration is 0 and changes sign. So the inflection points of the position graph line up exactly with the zeros of the acceleration graph. At those same times, the motion shifts between speeding up and slowing down.